All right, let's talk about net ionic reactions. So I'm going to start with what the words mean. The word net, if you've ever gotten a paycheck from somewhere official, it's usually got something on it that says net pay. And what that means is that is like your final pay after all the positives and the negatives, after you've gotten all of your pay accounted for, and then they take out Social Security and insurance and anything else that they're going to take out. Net pay is what you actually get. Okay, and then ionic, these are going to be reactions of mostly ionic compounds. There might be a covalent thing here or there. For the most part, they're going to be ionic compounds. Okay, and then we know what reaction means. And the key point here is that ionic compounds and acids, which are going to behave like ionic compounds in this case, that are dissolved in water, they dissociate. And what that means is that they break apart. They're going to act like individual ions. Instead of acting like a compound as a whole, they're going to act like two separate ions. Now, we had to deal with this a little bit when we had dealt with the molality in a freezing point depression situation, because when we have that many, that makes there be more ions actually dissolved, and it changes what that boiling point elevation or the freezing point depression is. Okay, kind of looks like this. So if I started with the sodium chloride crystal just like this, and I put it in some water, it pulls it all apart. So I actually end up with some sodium particles and some chloride particles, and I should probably have had the same number, but I didn't really pay that close attention, right? The sodium, now they're all jumbled together where they are, but they don't actually touch or care about each other anymore. So over here, when I've got a solid, these things need each other to stay packed into the shape. But when we dissolve them in water, they don't need each other anymore. And so they're just going to do their own thing and run all over the place. Okay, so important thing that we've got to understand is that this only happens, I'll underline that a couple times, okay, to aqueous substances. Okay, only happens to aqueous compounds. It will not happen to solids, to liquids, or gases, because in a solid, this crystal needs each other. Okay, in a liquid or a gas, those particles are set up in a different situation. It's only when they're dissolved that they've been pulled apart and that they're swimming around throughout the situation. Why do we care? Why do we need to do this? Well, if they're don't really have anything to do with each other, one of them might do something and it'll have absolutely no effect on the other one. Like if you're a bunch of kids in the lunchroom, not everybody in the lunchroom, so try this again. If there's a bunch of kids in the lunchroom and something happens, not everybody in the lunchroom was actually part of that something that happened. Okay, maybe the chloride's going to do something that the sodium just doesn't care about, and the sodium just keeps on being sodium. So we want to see what really happens overall, the net, after we cancel out all the extra stuff and all the stuff that we don't care about. But again, only happens to aqueous compounds, okay? Not solids, liquids, or gases. So let's look at an example on the next page, because I don't like the one at the bottom, okay? So if I've got this reaction that's written out like this, and this is how we would have put them in, right? I have some sulfuric acid and some what I think now is barium chloride, even though as an aqueous solution, it's really barium ions and some chloride ions behaving separately, but I put it in as barium chloride, so that's how I think of it. Okay, and I know that that's going to make hydrochloric acid, and that's going to make barium sulfate. Now, astute observers will see that I don't have this reaction balanced right now. That's okay, because I don't actually want to end up with this reaction when I'm done anyway. So I'm not going to bother balancing it before I start. What I am going to do is look at what really is here. Okay, I don't really have the compounds I think I have that I originally put in. Anything that is aqueous, so this sulfuric acid and this barium chloride and this hydrochloric acid, okay, these aqueous compounds really are behaving like separate ions. So I'm going to go out and list all of those ions and rewrite the reaction like that. So this H2SO4, I have hydrogen ions. Now, I know that there's two of them, but you know what? I just don't care right now. We're not going to deal with how many there are, just which ones are there. So I have some hydrogen ions, some H+, and those are aqueous. And I have some sulfate ions, okay, that have a 2- charge, and they're aqueous. Okay, and I know this compound dissociates, so I have some barium ions, and I have some, let's give it a phase label, and I have some chloride ions. Okay, in the product side, my hydrochloric acid is still really going to be behaving like two separate ions. So it's going to behave like hydrogen ions and chlorine ions. Okay. Plus, my barium sulfate here actually is a compound. It's a solid, it is a whole thing, and these barium ions are stuck and part of these sulfate ions. So we're going to leave that all together. Okay. And then we're going to look at what we really have. This is what was sitting in the container when it reacted, but did everything actually do anything? Or was anybody just sitting around minding their own business? This thing right here, this whole, we call it a complete ionic reaction because it has everything that's in the whole reaction. Okay. But is it really what goes on? Okay. If you look really close, you'll see this hydrogen ion right here. There's one over here too. When the reaction was done, the hydrogen ion was still itself. So was the chloride ion. It was an ion here, and it's still a chloride ion over here. Nothing has actually happened to this hydrogen ion. Nothing has really happened to that chloride ion. Okay, we call those spectators. Because, just a second, okay. Okay, we call those spectators, or also ions, there we go. Call them spectator ions because they just sat and watched. Nothing, they didn't do anything. They were not responsible for this reaction at all. They just sat around and watched the reaction. They were along for the ride so that they brought the sulfate and the barium to the party, but they didn't actually do anything. The barium and the sulfate are going to leave the party together, and the hydrogen chloride is just hanging around, minding their own business. Okay. Our net ionic reaction then is the reaction without those spectators in it. So that would be what I have left. So that's the SO4, 2 minus, is an aqueous substance, plus our Ba2 plus aqueous turns into the barium sulfate. Okay, and now we'll go ahead and balance this, but if you look, it's already balanced. Right? A lot of times that'll happen. What would have been kind of hard to balance up here gets a lot easier when we take out all the spectators and we don't care how many of them were hanging around. Okay, 1 barium and 1 sulfate turned into this barium sulfate. Let's try another example. I haven't written one out, but we'll try another one. Oh, sorry, one moment. This right here, it's called the net ionic reaction. And a lot of times when we talk about what really happens in a situation, it's the net ionic reaction we care about because all those extra spectators just get in our way. This is a much shorter, despite the fact that we've got the charges, this is a much shorter and simpler reaction. Okay, so what if I had something like, I took, solid copper plus silver nitrate solution, right? If I have a single displacement reaction like this, where I end up with some silver that's solid plus copper nitrate, okay, that was an aqueous solution. What if it was something like this? Okay, well, again, we go through and we take only the aqueous solutions and we break them into ions. So I had copper, it's still a solid, right? Solids don't change. Plus, this is aqueous, so we break it apart. Silver, okay, silver ion is positive, plus nitrate, there's 3 there, NO3 negative, aqueous, becomes, this silver isn't a solid on this side, okay, plus I had copper 2 ion, was aqueous plus some nitrate ions, also aqueous. Okay. Okay. Can you spot the spectators in this reaction? Now, some kids, often, a lot of kids will tell me that everything's a spectator. Everything's the same. The only thing that doesn't change at all in the entire reaction, though, are these nitrate ions. Right, these nitrate ions haven't done anything. Now I know it looks like I've got copper here and I've got copper there, but here I had a solid piece of copper and over here I have copper ions. This is actually a chemical change in the copper. Same thing for the silver. Having silver ions here and solid silver there are not the same thing. So I keep them. Okay, so we end up with solid copper plus silver ions, making solid silver plus copper ions. Okay, so now I need to balance this reaction again, and once again, first glance, it looks balanced, but I have more charge on this side than this side, and I have to get those balanced as well as the elements. So I've got the elements balanced, but I have to get those charges balanced too. So to get this 2 plus to balance with this over here, I'm going to put a 2 in front of the silver. Okay, and that means that I'm going to have 2 silver atoms right there. Okay, again, usually net ionic reactions really balance very easily. Once again, you take all the aqueous substances, we break them into their parts, we rewrite it without any spectators, okay, and then we balance. That's all there is to it.